Now we need to see how this applies to real physics problems. Did everybody get a packet? Okay, so now we need to see how this is going to work for us. Linear motion in 2 dimensions, vectors and vector addition, vectors and scalars. We've already said that something that we call a vector is basically one of these little arrows, right? That's a vector. But what's special about this is that this vector has a direction, okay, and it has a magnitude. Hopefully you remember from Despicable Me, vector had a magnitude and a direction, right? I have magnitude and direction. So a vector quantity is any quantity that has both a magnitude and a direction. Okay? If I am in 1 dimension, I don't really have to worry about the direction as much because it's only one thing. It's either positive or it's negative, right? But if I'm in 2 dimensions, we're going to have directions that are at angles to our axes. What is a magnitude? What is a magnitude? What? A mega attitude? No. That sounds like something Donald Trump would say. What's a magnitude? It's just a value, right? It's a value of some quantity. The value of some quantity. So if I said 10 meters per second to the east, what part of that would be the magnitude? 10 meters per second to the east, what part of that's the magnitude? The 10, right? The 10 is the magnitude, okay? The value of some quantity. Okay, what are some quantities that you are aware of that have both a magnitude and a direction? What have we always talked about as having direction in our quantities so far? Acceleration, okay? That's one. What else? What are the 3 other basic quantities for motion? Oops.
Velocity.
Okay. How did that get there? Why is it? Okay. Even with my good computers, I'm having technical difficulties now. Okay, sorry about this. Okay, finally. Acceleration. Someone said velocity. What else? What are my two other ones? That's not a vector. It doesn't have dimension. It doesn't have a direction. That'll be a scalar quantity. Come on, guys. What are our four main things of motion? That's not one of them.
That's all I remember.
How is that possible?
I don't know. I'm just saying stuff. At least I said something.
No. What do I have to know about anything before I can tell what motion is? Where am I at in space? What's that called?
Position.
Position.
Basically what I said.
Did you say position?
No.
Okay. Then what is change of position?
Displacement?
Displacement. Thank you. Okay? Before I can do anything, I have to know what my position is in space, right? And then I can figure out how far I went from that point. And that is my displacement. Not how far I traveled to get to that point, but how far I am from that point, right? And then, how fast did I get there? How much displacement did I have during a certain amount of time? That's my velocity. And then, how did the velocity change during a certain amount of time? That's my acceleration. One other quantity that we've used that has direction and a magnitude is the force. We've used forces. Okay? Remember, the sign of the vector quantity only represents the direction, not the value. Okay? So if I had a velocity of negative 10 meters per second, that's not a value of negative 10, that's a value of 10 in the negative direction. What was your question, Joe?
I think I missed something about magnitude.
Oh, the value of some quantity? Okay. So, what if the motion is on a two-dimensional frame of reference? How will we represent the direction then? I've already said it, but it's not just positive or negative now, because if I have a motion that's like this, is that a positive or a negative motion? We don't know. So how would I figure out what direction that is? What would I designate that tells me what direction this is? Maybe an angle? Okay, I'm moving at 45 degrees from the positive x-axis. What if the motion is on a two-dimensional frame of reference? How will we represent direction then? By stating an angle for the direction of motion. By stating an angle for the direction of motion from a reference axis. By stating an angle for the direction of motion from a reference axis. Usually it's going to be my positive x-axis. Okay, and in this case that would be an angle of 45 degrees. So I'm moving at a certain rate in a direction of 45 degrees from the positive x-axis. Okay? That would be how I would state that. A scalar quantity is a quantity that only has magnitude. It only has a value. And we've already said one of these.
Let's go.
That is time. Okay? 10 seconds doesn't have a direction, does it? It's not positive or negative. It just is. We also talked about something that corresponded to the displacement that does not have a direction. If I'm just talking about the number of units that I have traveled instead of the direction that I've traveled in, what am I talking about? Not displacement, but distance, right?
Yeah.
Remember, if I go from here to here, that's my displacement. But if I do this to get from there to there, that's the distance. Okay? It doesn't have a positive or negative value. It just has a number of units. Likewise, since speed is based on distance rather than displacement, speed is also a scalar value. It does not have a direction. Velocity has a direction because it's based on displacement, but remember, speed equals distance divided by time, whereas velocity equals displacement divided by time. Okay? What are some other things that might have just a value and not a direction? Mass. You agree? Mass does not have a direction. Mass just has a value. Volume would also be another thing that just has a scalar quantity. Density would be something that would just be a scalar quantity.
Is that for often?
Well, I was just, yeah. Right, mass per volume is density, isn't it? So, can a scalar quantity ever be negative then? No. If we give it a positive or negative value, it becomes a vector. Okay? If I give it a positive or negative value, I'm giving it a direction. No, that's not it. Can a scalar ever be assigned motion at a number of degrees from a reference line? No. This also would give it direction and make it a vector. So once I assign a direction to some value, I am changing it from a scalar value, something that only has a scale, to a vector. Okay, vectors can be represented graphically by an arrow. We already know this. The direction of the arrow represents the direction of motion, and the length of the arrow represents the magnitude. If drawn close to scale, direction and magnitude can be summed using geometric methods. Okay, so if I have one vector that's like this, and another vector that's like this, So again, suppose we're talking about something that is navigating in this direction and something that's pushing it away from its course in that direction. Remember, this represents, the length of this represents the velocity that's going in this direction. The length of this represents the velocity of something that's pushing it away from its current course. And we said that we could add those two vectors together. And this literally would represent the actual velocity. Okay? Now notice, what's the only circumstance where if I had, let's say that this is 10 meters per second, and let's say this is 5 meters per second, what's the only circumstance where I can add those two numbers directly? 10 plus 5 gives me 15 meters per second. What's the only circumstance I could do that? Yeah.
Going in the same direction.
They were going in the same direction, right? If these two were going in the same direction, then I could add those directly and get 15 meters per second. But I can't do that if it's at some other angle, because I don't know how much of this is pushing it in the horizontal direction, right? I don't know how much of it is being used to push it in, not in the horizontal, in the angled direction. But if it's drawn close to scale, direction and magnitude can be summed using geometric methods. How would an old-time navigator have done this on a map? What would they have used? What tools would they have used? A compass and, yeah, what else? Maybe a ruler or maybe a protractor. So use a compass, ruler, and protractor, right? They didn't have any computers, they didn't have any calculators. They had to do this all by hand and a pencil and a paper, right? If you were a navigator on a ship, you were very skilled at doing stuff like this. Now, vector quantities are often symbolized in text by bold-faced type and an arrow over the top of the symbol like this. When just representing magnitude, non-bolded symbols with no arrows is used, this symbolization will not be a requirement in this class because it's really annoying to try and write out things in bold type with an arrow over the top of it. So, but if you see something like this with bold type and an arrow over the top of it, just know that that represents a vector. Just like any other quantities, vector quantities can be added together. And this is called vector addition. Okay? I'm not adding numbers anymore. I am adding numbers and directions, which usually blows people's minds. How do I add direction? Okay? Because vectors include both magnitude and direction, you may not be able to just add or subtract the values. Okay? So, consider the following two situations. You walk 100 meters to the east, then you walk another 250 meters to the east. Draw vectors representing both displacements. Okay, you've got a space here, so we're going to say, let's see, D1 equals 100 meters. D2 equals 250 meters. Now, if I really wanted to do this correctly, I would get out a ruler and measure how long D1 was and make sure D2 is 2.5 times the length of D1. Okay? Because I'd like to be able to use a ruler to tell me how far I went. Okay, so we drew vectors representing both displacements, and we drew to scale and we labeled them correctly, D1 and D2. Then draw a vector representing the sum of the displacements. There's a vector representing the sum of the displacements. D equals D1 plus D2 equals 100 meters plus 250 meters equals 350 meters. Again, this is the only circumstance where I can do this, because they're both in the same direction. Create a mathematical formula to find this vector sum. Our diagram's purpose is specifically so you can create a mathematical formula that will accomplish solving the problem. Okay? Using what I see here, I can say that D equals D1 plus D2 equals 100 meters plus 250 meters equals 350 meters. And you will be required for quite a while to do this completely. Does this vector sum appear to be the result of simply adding the values of the two individual vectors together? And the answer for this one would be yes, right? It does appear that way. And we're going to call this vector sum the resultant. Not the result, but the resultant. Okay? That would be an example of a vector diagram in one dimension. I'm only going in one dimension, right? But now I'm going to walk 100 meters to the east and then 250 meters to the north. Okay, so I'm going to mess things up here. So I'm going to draw vectors representing both displacements. So I'm going to draw a vector that says D1 equals 100 meters. Whoops. Am I going to the north first or the... I went to the east first. Okay. So 100 meters. And then I'm going 250 meters to the north. D2 equals 250 meters. Okay? So there are my vectors representing both displacements. They're drawn to scale and labeled correctly. Then I'm going to draw a vector representing the sum. Now, how do I add these two things together? I just connect my starting point with my ending point. And that will give me the displacement from here to here, right? That's what this is, right? I went from here to here, but I used this path. My displacement is this, though. Okay? And I'm going to call this D, and I'm going to give it a question mark, and I'm not going to solve it on the diagram like I did on the other one, because there's not enough room. Now, knowing this is the right triangle, how am I going to find that distance? We've done this before. Okay? And I use the what theorem? I use the Pythagorean Theorem, right? So I'm going to create a mathematical formula to solve this vector. I'm going to say D equals the square root of D1 squared plus D2 squared, right? That's how I use my Pythagorean theorem. Because I know that D squared equals D1 squared plus D2 squared, D is going to equal the square root of D1 plus D2. Let me... Okay? Equals the square root of 100 meters squared plus 250 meters squared. And yes, I am going to require you to use units all the time. And follow this process all the time. So when I do this, I get 269 meters. Did anyone else actually do that calculation? Is that what you got? Good. Okay. Yeah, we'll just round it to 269 here. Okay? So, any questions about this so far? Here's what I want you to understand. This is the difference between adding two numbers and adding two vectors. When we add two vectors together, the mathematical notation showing the sum is still the same, no matter how we end up solving the sum. If I want to use mathematical notation to show the vector sum, I would still write it as a sum. Okay, now I didn't put that up there because I didn't want to confuse things, but to say this is a sum would be just simply to say delta D equals delta D1 plus delta D2. Remember, delta also means displacement for displacement. Or I could have simply written D equals D1 plus D2, because that's also a label for my vector. Now, notice I'm not adding them directly here. What I'm doing to find this sum is use the Pythagorean theorem. But if I just wanted to represent the sum itself, the vector sum itself, I would say D equals D1 plus D2, recognizing that they're vectors and that I might have to not use the values added together. So in vector addition in one dimension, to find the sum, we simply added them together. In the second situation, to find the vector sum, we use the Pythagorean theorem. Okay? What was the distance for both walks? Not the displacement, but what was the distance for both walks? 350 meters, right? But the displacement for the first walk was 350 as well, but the displacement for the second walk was 269. Okay? So again, when you add vectors, you may not just be able to add or subtract the values of the vectors together. We should be able to get through vector addition in one dimension here. Now, because only directions are positive and negative in one dimension, vectors in one dimension can be added together in simple arithmetic fashion. I can add the numbers. The diagrams below show a graphical representation of a vector addition called a vector diagram. Okay? This is a vector diagram, and this is a vector diagram. As much as possible, our conventions are the vector is drawn to scale. This allows measurement with a ruler or protractor or for angles directly from the vector diagram. If I needed to, we're not going to do that because we don't really need to do that because we've got calculators and computers, right? All added vectors are appropriately labeled with the type of vector and the value. And you can use your own system of subscripts if you want. You don't have to use mine, but you do need to indicate individual vectors with subscripts. And then the vector representing the sum, again, is called the resultant. This should also be labeled and has no subscript. Okay, so for this, Chase, can I get you to shut that door? So for this particular motion, notice somebody went 8 kilometers and then that same person went another 6 kilometers. Okay? And the resultant is the sum of those two vectors. 8 kilometers plus 6 kilometers equals 14 kilometers. Okay? In this case, the person walked 8 kilometers in the first motion and then displaced negative 6 kilometers. That doesn't mean they went a value of negative 6. It means they went a value of 6 in the negative direction, right? But we can still use that. We can say dA plus dB equals 8 kilometers plus negative 6 kilometers gives me 2 kilometers. The purpose of this diagram is to give you a formula that you can solve. Now, this looks really easy in this circumstance, okay? But we're going to have a circumstance where it's not quite as easy. Don't know what that is. Okay, I wish that weird stuff would stop popping up. Okay, either directly on the diagram or somewhere off to the side in workspace, a formula and work that solves the addition should be placed. For any calculations involving vectors in a negative direction, treat this as adding a negative value for now rather than subtracting. Graphical representations of vectors, their values and directions should always be supported by accompanying mathematical analysis. And labeling things in this way allows you to create formulas that show you how to accomplish the vector addition. And this may seem silly when all you're doing is just adding two numbers together, but even this simple situation can get confusing. And let's illustrate what I mean by that. Okay, so you walk 800 meters to the east, right? That's my first displacement. You then walk some more and end up in a position 200 meters to the east of where you originally started. Okay? Now, I gave you one of the motions, and then I gave you your resultant there. Okay? I didn't give you two things to add together. I gave you one of the things that you're adding, and then I gave you the answer. Okay? So how do you think you might diagram on this the second motion? What's delta D2 going to look like? Any thoughts of what the second diagram arrow is going to look like? And the way to think about this is, what do I have to add to this to get me to this? What do I have to add to this to get me to this? What should that second vector look like?
600-meter arrow pointing the opposite direction.
Exactly. Starting from this point right here, I'm going to have this motion, delta D2 equals negative 600 meters. Not 600 meters that's negative, but 600 meters in the negative direction, right? This is what I had to add to this to get me to my final spot. Okay? Come on. Okay, so you must be able to create both diagrams and mathematical statements that correspond to those diagrams that match. How would we label the second motion? We've already said delta D2. So draw a displacement arrow showing the second motion on the diagram. Now we need to create a mathematical statement that solves for this. So I know delta D equals delta D1 plus delta D2, right? I can get that, and I know that, but I don't want delta D. What is it that I want? I want delta D2. So now I can say delta D2 equals delta D minus delta D1. Okay? And now I can say delta D was 200 meters and subtract 800 meters. And guess what? I get my same value, negative 600 meters. Okay, so the math has to support the diagram. The math has to support the diagram. Okay. Notice the two vectors we're adding together will always be placed on the diagram in a tip to tail fashion. Okay, this is tip to tail. Right, here's the tip, and there's the tail. Tip to tail. Okay? These vectors should have subscripts. The resultant vector shows the sum of the two vectors, and it should not have a subscript. If you follow this convention, you will always be able to create mathematical formulas that make sense and help you solve the problem, no matter how difficult. We've already seen a situation where if we have a strategy, even if we don't know how to solve the problem, the strategy leads us through the process, right? It's going to be the same way here. If I have a correct strategy, I don't have to know how to solve the problem. The process leads me through it. Okay, so we're not going to have time to go through this next problem here. We'll stop here. And I'll take your notes, because I'm not going to ask you to do anything over the next 2 days. What is today? Tuesday?
Monday.
Monday. Oh, crap. Just the beginning of the week?
Yeah.
Does this make any sense at all? A little bit? A little fuzzy? Any sense or a little fuzzy?
That'd be funny if we like show like country like Bulgaria. And then he just like what a year. Just like reward. Is that like this hearing? He's just sitting there like this, this.